Hi students, today we are going to see the chapter sound of CBSE class 10. Now we go through the presentation that I'm making here. Basically in this chapter we deal with the sound, its propagation, of course some of the characteristics of the sound, then different ways of producing it. Of course finally we end up with the audible range and human ear details, etc. Now, see, first part would be like production of sound. As you are aware, sound is always produced from the vibrating body. So, you can see, now here there is a tuning fork, which when given, so when it is beaten by a hammer, it produces oscillations. So therefore, the tuning fork, as and when it is hit by hammer, it produces vibrations. So vibrations are produced. As such, you can hear the sound of it. So therefore, a vibrating tuning fork will in turn, so it can generate some sound waves, and because of the sound waves, you can observe, as in the figure, you can observe that a small thread, I mean, a table tennis ball connected to a thread, a fixed thread. No, it will just displace. So it is the sound waves that displace a table tennis ball connected to a thread. So therefore, we can easily say that sound is produced from vibrating body. Here it is a tuning fork that produces oscillations or sound waves. Now coming to the propagation of sound, see for the propagation of any energy, the sound is a form of energy, just like light. See, for the propagation of any energy, we need a metallistic medium. Here, sound also requires a metallistic medium, like air and the other things like what else? Like see, it can be air or any other metallistic medium. See, for its propagation, it requires. So therefore, end of the day, how actually it is propagated? If you look at when an object vibrates, now the particles around the medium also vibrate. So therefore, the particles in contact with the vibration object is first displaced from its equilibrium position. So therefore, from their mean position, they change, they vibrate, and then it then exerts a force on the extant particle. So therefore, it is not, end of the day, it is not the wave that moves, like only the vibration is transmitted to the next particle. So from the mean position, the particles of the medium just they vibrate, and this disturbance is just transferred to the next subsequent particle, and so on and so forth. So this is how propagation happens. But end of the day, it is not the total disturbance. I mean to say, the wave will not propagate, only the disturbance is propagated through the vibration of the particles. So therefore, we can see here, disturbance produced by the vibrating body travels to the medium, but the particles do not move. That is very important point we have to note down. Next thing is a wave, we can say it is a disturbance which moves through a medium. That means wave is always a disturbance. We can also define wave as a form of energy, that is a flow of energy. Okay, so sound is considered as a wave, and and sound waves are produced to the vibration of the particles of the medium. Now, so that is the reason why they are also called mechanical waves. Next thing is, in the air, exclusively if you look at, so there are two things happening here. One is compression and rarefaction. So what is this? Air is the most common medium through which sound travels. So when a vibrating object moves forward, say as shown in the figure, like here we have a tuning fork moving, when it is moving forward, then it pushes and compresses the air in front of it, okay, forming a region of high pressure and called compression. So therefore, as the name implies, compression is the region of high pressure, and compression moves away from the vibrating object. Okay, so therefore, when the vibrating object moves backward, it forms a region of low pressure. Like that, as the vibrating object moves forward and backward, the regions that are formed with high pressure and low pressure are called compression rarefaction, which you can see in the figure. So here there are compressions and rarefactions where the particles, they are compressed as the name implies. So the surrounding region is compressed because of the movement of the vibrating object. Now, so they are called compression rarefaction accordingly. Now, next thing is a vibrating object producing a series of compression rarefactions. In this slide, you can very easily say in the beginning there is a compression and then a rarefaction. So like that, at different instants of time and regions, there are compressions and rarefactions. Next thing is sound. That's what I told. Sound requires a metallic medium to travel. So this needs to prove the same. We can conduct an experiment wherein we can take an electrical bell and which is there inside the bell jar. You can see, as you can see in the figure. So there is an electrical bell over here in the bell jar, and of course it is with other settings like setups like arc and other things like. Only thing is when you see to prove that exactly sound requires a metallic medium. So here we can easily prove that once this electrical bell is made to ring, so it is audible. But when you have a vacuum pump beneath, so through which the air can be evacuated. So as and when with the help of a vacuum pump, if the air is evacuated, so then see the vibrations or the sound from the electrical bell will not be audible. So this clearly shows us that see, sound obviously requires a metallic medium for its travel. So here in this, initially we make the electrical bead to ring, so in the normal position, and then in the next phase, when through the evacuation pump or vacuum pump, when the entire air is evacuated, no longer the sound is audible. So that clearly says that sound requires a metallic medium for its travel. Now, sound waves are longitudinal, whether they are longitudinal or transverse. Just now we have seen that it is end of the day, it is a particle of the medium that vibrates. So therefore, a wave is actually a progress forward with the vibration of the particle. So therefore, so with the vibration of the particle. So thing is that, yeah, now we have to see, we have to tell whether it is longitudinal waves or transverse waves based on the movement of the particle. Now here you can see, first we discuss about longitudinal waves, where in the case of longitudinal waves, you can see here the direction of propagation of the disturbance basically. So the waves, see in these waves, particularly when the particles move backward and forward, back and forth, parallel to the propagation of the disturbance. See, if you see, if they move parallel to the propagation of the distance, that is called longitudinal, and on the other hand, on the other hand, so when actually the disturbance is perpendicular. Okay, so therefore first case is where the particles move back and forth parallel to the direction of propagation, and they are called longitudinal waves, as the name implies, longitudinal along the length. And there is another kind of waves called transverse waves, where the waves they actually produced due to the vibration of the particles oscillate up and down perpendicular to the propagation of the direction of disturbance. So if the disturbance is in a particular direction, that means the propagation of the disturbance. So when the particles vibrate along the disturbance, that is called longitudinal. On the other hand, when the particles vibrate perpendicular to the direction of the disturbance, that is called transverse waves. You can see the same in the figure. Okay, longitudinal and transverse. Right. Next thing is characteristics. If the very important thing is when you have once the sound waves, once the sound energy that is described as a wave, then for each and every wave there are some characteristics to be understood. First thing is there are three basic characteristics we need to understand. What is frequency, amplitude, and speed? So what is frequency? What is amplitude and speed? You can see. So before that, we just try to understand that there are the two terms called crest and trough. So in the case of crest, actually, no, because compressions are just now we have seen compressions are formed where regions are in the regions of high pressure, and of course density, where the particles are crowded and represented by the upper portion of the curve. So here, so you can easily see exactly at the upper portion of the curve, if you see the medium, the particles are very much dense, and of course they are compressed. Of course, similarly at the negative, in the negative half cycle, that is in this second portion. in the negative half cycle, there is a rarefaction. So therefore, so we can also define a crest and trough here in order to define wavelength and frequency. Initially, we define crest and trough. So therefore, crest is the upper portion of the curve and trough is the lower portion of the curve. Now, if you want to have defined wavelength, actually it is a distance between two consecutive compressions or two consecutive rarefactions. I mean, between two crests or two troughs, it is said to be this one, right? Okay, that's what we call as a wavelength. As the name implies, it is a length of one complete wave or complete cycle. So as shown here, actually, it is represented by the symbol lambda. So therefore, it is a distance between either two crests or two troughs. Now, next thing is, so first you define wavelength as actually it is a distance between two successive crests or troughs, or two peaks, two positive peaks or two negative peaks. The next thing is we need to look at frequency of sound waves. So as the name implies, frequency is actually is the number of cycles made, number of cycles per second. So given a time period, we can define frequency as the number of cycles per second in a given unit of time. So therefore, you can easily say here what is the frequency and what is time period. So you can observe in the figure that short wavelengths means lots of waves and the long wavelengths means fewer waves, right? So therefore, frequency actually is low frequency in the case of long wavelength, and in the case of short wavelength, obviously there is high frequency. That means if the number of cycles are more, then it is short frequency, and on the other hand, the number of cycles are less, it is said to be less frequency. Now, so given these two characteristics, like just now we have seen wavelength and frequency, the next characteristic to be understood is time period. So time period, how it is defined? The time period is the time taken to complete one complete cycle. So here, as I told you, the complete cycle is actually between, it is a cycle, I mean distance between, when I say complete cycle, one positive half cycle and one negative half cycle completely. So therefore, the time taken for the change in the density of the medium from a maximum value to a minimum value and again to the maximum. So that's what I have been telling, one positive cycle, one negative, and again a positive cycle. Like that is the time period of the sound wave. You can see here what is the time period. So time period actually represented by the symbol capital T, it is always reciprocal of the frequency. So therefore, time period is a time taken for one complete cycle. So one complete cycle, when I say one positive half cycle and negative half cycle, not even for the next positive half cycle. So from here to here, as shown in the figure, the time taken, because on the x-axis we take time, and on the y-axis we take either volt, I mean, its amplitude, whatever it may be, pressure. So therefore, one complete cycle, the time taken for one complete cycle is said to be time period, and mathematically it is given as 1 hour frequency, reciprocal of frequency. Then what is amplitude? Amplitude is amplitude is the magnitude of the wave at a particular instant of time. So therefore, it is the magnitude of the wave at a particular instant of time is said to be amplitude. So you can see here on the wave, actually there is a green spot here. So on the from the x-axis, whatever the vertical distance is, that is said to be amplitude of the wave. Okay, so it is nothing but it is the height of the crest or trough, or it is simply magnitude. So here SI unit would be the same, just like as density or pressure, whatever may be its unit generally. So we say generally sound waves because they are, generally we talk about the strength of a sound wave as in terms of decibels or like that. Okay, next. So other important characteristic that differentiates some of the hearings, like human hearings. Some people like between a male voice and a female voice that differentiates is pitch and loudness. So the pitch of a sound, it is also called as shrillness or flatness, depends on the frequency of vibration. So for female voice, the pitch is more, and if the frequency is high, the sound has high pitch, and if the frequency is low, the sound will be having low pitch. So then what is loudness? Loudness, it is the intensity or magnitude of the wave. So it is actually the intensity, that means intensity or magnitude of the wave is said to be loudness, how loud the signal is. So it is nothing to do with frequency, it is only the amplitude. Next. Now see, next thing is the loudness of sound depends upon the amplitude of vibration. As I just told you, it depends on the amplitude of the vibration. So if the amplitude is bigger, then the sound is loud, and if the amplitude is smaller, that sound is soft. So that is a differentiation between a male voice and a female voice. For male voice, vibration, I mean, the loudness is more. For female voices, it is the shrill or the pitch is more. Now, next thing is speed of the sound. Actually, so whenever a particular energy is there and it is propagating in a medium, it is important for us to exactly calculate the speed of it. with what speed it generally progresses. For light, we have very much defined the T into 3 into 10 power 8 meter per second is the speed of the light in vacuum or free space or air. For sound also, we have a standard value that is given by an equation called V is equal to F lambda or mu lambda. Okay, so we can calculate the velocity or speed of a wave with wavelength and frequency. So given the wavelength and frequency, we can calculate. Now, therefore, what we need to do is actually it depends. The speed depends. The speed is not the same in each and every medium. So if the temperature of the medium is more, speed is also more. So generally, for standard conditions like at 25 degrees or 30-degree room temperature, we calculate the speed of the sound. So therefore, speed of the sound is different in different media. So we only actually we have seen the dependence of the speed of the sound on different parameters. We exactly will come to know it is around 344 kilo. Yeah, 344. Yes, when it comes to its magnitude, per second. Yeah, 344 meters per second is the exact speed of the sound for a particular temperature. Next thing is reflection of the sound, because just whenever we have seen sound as propagation of some waves, just as in the case of light waves, here also, so whenever there is a change of medium, so there is a chance of reflection, and then we also study the chance of refraction or any absorption. When you look into that particular aspect, actually like light and sound wave also get reflected. That means they bounce up into the same region. So therefore, we have an activity here with two pipes of the same length, and when arranging them on a table near a wall or a metal plate. So, and you're keeping a clock near the open end of the pipe. So here you can see that when you try to hear the sound of the clock to the other pipe by adjusting the position of the pipe. So now measure the angles of incidence and reflection. Not only for light, actually in each and every case, angle of incidence, is almost equal to the angle of reflection, right? So angle of incidence is always equal to the angle of reflection. Okay, and of course, second law also, the same here also we can very much, that is also applicable, that the incident ray, reflected ray and normal, they lie in the same plane. Next thing is echo. What are echoes? Echo is actually, it is a reverberation of sound, or I mean to say that is, when I say echo, it is reproduction of the same sound. So particularly when you are near to some reflecting surface like a tall building or a mountain, we hear the same sound again and again. So this process is said to be, this sound which is here is called echo. So basically it is caused totally exclusively because of reflection of the sound. Now if I say to hear an echo, what is the minimum distance that it must be? So the time interval between the original sound and the echo must be at least 0.1 second. Please try to underline this point. To hear an echo clearly, the time interval between the original sound and the echo must be at least 0.1 second. So because 0.1 second lies due to persistence of sound, so that must be there. Otherwise, we cannot hear an echo. And that totally depends on distance time speed calculations. Around, as I told you, it is 344 meter per second. It is the speed of the sound in air when it is taken. Okay, into 0.1 second is the time taken for its to receive an echo. So therefore, the minimum distance at which exactly these mountain or taller buildings, the tall buildings lie, they have to be 34.4 meter. That means for going and coming back. So therefore, minimum distance would be 17.2 out of 34.4 exactly divided by 2 comes to 17.2. So therefore, the total distance traveled by an echo is 34.4, and the minimum distance to hear an echo is 17.2 meter. So in the same similar lines, we can also define reverberation. So echoes may be heard more than once due to repeated or multiple reflections. So this causes persistence of sound called reverberation. So the persistence is said to be reverberation here. Now the next thing is multiple reflection, that again whatever we observe in light, here also can we observe the same. So here generally sounds from the human body also they also get multiply reflected, particularly in megaphones, horns, musical instruments like trumpets and shennais. Like, okay, so not only stethoscopes and all. Therefore, they are designed to send the sound by multiple reflection in a particular direction without spreading in all directions. So they are designed in such a way, right? So the doctors in particular, they listen to the heartbeat of, you see, heartbeat of heartbeat that reaches doctor's ears by multiple reflection only. These are the cases you can see in the picture. A stethoscope is mentioned, a yes, and we have generally speakers, or what we say, yeah, like other things, Chennai and horns, musical instruments are shown here, right? Now, so coming to the range of hearing, so there is, we already studied in earlier classes that is the audible range for human ear is 20 to 20,000 hertz. Yes, 20 to 20,000 is the audible range, below which actually human ear cannot sense the particular frequencies. So below 20 hertz or beyond 20,000 hertz, human ear cannot get. So therefore, this is what I can take 20 to 20,000 hertz, not 2,000 hertz, exactly it is 20,000 hertz, right? But up to 2000 hertz, yes, okay. So very much they can hear, right? So therefore, about 20,000 hertz. I mean, there is a small printing mistake here. 20,000 hertz you can take it as. No, it is 20,000 hertz is called ultrasonic sounds, and below 20 hertz it is called infrasonics. So some of the animals can listen to these infrasonics and ultrasonics, but whereas human ear cannot listen. Animals like dogs, elephants, rhinos, right? They can hear. Similarly, some of the insects like no, even bats use reflection and ultrasonic sounds to detect an obstacle or its I mean food, like it pre means no, they identify their own food like this by sending some ultrasonic sounds and all. Now the ultimate uses of ultrasonic sounds, where particularly we use ultrasonics, are used to clean objects like electronic components to be cleaned are kept in a cleaning solution, and ultrasonic waves are sent to the solution, and they are used to detect cracks in a metal block. Very importantly, to detect the metal cracks in the metal block, and they are sent through a metal blocks. If there are any cracks, the waves are reflected. Otherwise, okay, they'll be sent, transmitted. Ultrasonic sound is used in ultrasound scanners for getting images of internal organs of the human body. Nowadays, all hospital facilities, we are seeing that. Now, ultrasonic sound is used to break small stones formed in the kidneys into fine grains. That one advantage is there with the ultrasonic sounds, right? Lastly, we have sonar, like so stands for sound navigation ranging. It's a device which uses ultrasonic waves to measure distance, right? So direction and speed of the underwater projects. So therefore, particularly in the underwater projects, to find the distance, sonar is used. So it will have a definite transmitter and a detector installed in ships. So therefore, transmitter produces ultrasonic sound. Any system for that matter should have a transmitter, reflector, and a medium. So therefore, a receiver and a medium. Ultrasonic sound waves which travel through the water, and after striking the object in the sea bed, again it's reflected back to the detector. The distance of the object can be calculated by knowing the formula 2d is equal to v into t. That means 2 times the distance. Unless and until it travels 2 times the distance, it cannot be on the same plane. So therefore, you can see in the picture, the transmitter is here and the receiver is here. So therefore, it has to travel all through to the depth of the sea, and again it has to reflect back. So therefore, we can easily 2d, if the distance is taken as 2d, and with what velocity, if you want to know, 2d is equal to velocity into time, and d is equal to velocity into time by 2. So this is how the distance is calculated, because yes, with the sound, speed of the sound wave in water. Yes. Lastly, we have structure of the human ear, that is how human ear can listen to the voices. Outer, see, we have a very sensitive organ called human ear, like outer ear called pinna collects the sound waves, but sound waves pass through the ear canal to the thin membrane called eardrum, very sensitive part. So eardrum vibrates, and the vibrations are amplified by the 3 bones of the mid. So eardrum will have 3 bones, that is, one is middle ear called hammer, anvil, and stirrup. Middle ear then transmits the sound waves into the inner ear. So that's what very important. Please underline that. And in the inner ear, sound waves are converted into electrical signals. To convert, to understand anything, it needs to be converted into electrical signals. So only it is inner ear that converts. So by okay, and sent to the brain through the auditory nerves. So this is how a sophisticated mechanism is made of our inner ear. Okay, so and we are able to hear very this what the audible range sounds and all. So these are the important concept as far as sound are concerned. So here, okay, I think you enjoy this chapter a lot with the characteristics and all. And these are the basics of sound waves. Thank you.